Good afternoon, good evening, all. So now we'll go for the third part of body plot, right? The next thing of body plot, and we had seen in the last two lectures, if it's gain, how to plot the body plot, right? Then if it is pole at origin, we had seen gain. The gain plot was just gain. The magnitude plot was a straight line. Okay, when pole plot was there, when a pole was at origin, we had seen that yes, there will be drop and the slope will be minus 20 dB per decade. Then we had seen for zero at origin, and we had seen over there the graph will be this one. That means the slope will be 20 dB per decade. Then the next thing was real pole, and we had seen that yes, it will be till omega 0 cutoff frequency or break frequency. It's a straight line. At this point it is 3 dB, and then it decreases with so if I'll draw the line, yeah, it decreases with again 20 dB minus 20 dB per decade. Just we are revising. Okay. So practically the graph is going to be this thing. Then real zero, right? It was, yeah, I forgot to draw the phase plots, right? It was 0 for k greater than 0, and it was 180, 0 degree, 180 minus 180 degrees for k less than 0. Over here for this, for pole, it was minus 90. For this it was plus 90. Correct. Here it was 0, 45 and 90. Correct. And for this it was real 0 के लिए 0, 45, and then at this frequency it was 45, and then it was 90. Yeah. Then for real 0, we had seen that yes, it goes like this and plus 3 dB at this point. So real graph, we'll see actual graph will be this one, and this line is of plus 20 dB per decade. And now we want to go ahead now, right? For the next one is the complex conjugates. When you are having, that means your poles or zeros are complex. In that case, what is going to happen? Now very much clear why I have drawn all these things. Keep in your mind, exact mirror image you are going to have, right? Whenever you are talking about zero and pole comparison. So minus 20 plus 20, it was minus 20 on this side, minus 3 dB ka point over here, plus 3 dB, and slope was plus 20 dB per decade. See the phase plot also, 0, minus 45 minus 90, 0 plus 45 plus 90. So exact mirror image of both the plots we are going to get, and that's why now the next thing, I am not going to go for the complex zeros. I'll just go for complex poles, and I'll tell you how to draw it for complex zeros. If you are interested, definitely you derive the thing and you'll find yes, we are getting the same result, right? So I'm talking about complex poles now. Yes. So complex poles means definitely you are aware of, many a times we had seen second order system, correct? Two poles we are talking here about which are complex. You may have n number, right? But time being we are talking about 2. So we'll say omega n square is square plus 2 zeta omega n s plus omega n square. Correct? So yes, we are supposed to substitute S is equal to j omega because we are talking about frequencies. So GH j omega is equal to omega n square, here j omega bracket square, 2 zeta omega n j omega plus omega n square. So omega n square upon omega n square minus omega square j square, right, plus 2 zeta omega n omega j. So we'll try to put 1 over here, so will be easy for us to separate it into real, that thing into real and imaginary parts. Okay, so when I'm dividing by omega n square to the expression, I'll get 1 minus omega upon omega n bracket square plus 2 zeta 1 omega n cancel out, omega upon omega n j. Okay, so now to get the real part and imaginary part separate, we'll rationalize this thing. So we are going to get, I'll start from this, so will be easy. So you are going to have 1 upon yeah. So 1 minus omega upon omega n square plus 2 zeta omega upon omega nj, right, into 1 minus omega upon omega n bracket square, right, plus means minus over here, 2 zeta omega n j, same term, 1 minus omega n bracket square minus 2 zeta omega n j. Let me separate this first. Yeah, so we are interested in writing the denominator, right? So when you are going to square it, just a minute, yeah, so we'll have is equal to, now this is the numerator, so 1 minus omega upon omega n square minus 2 zeta omega upon omega nj divided by, yes, now see this thing, whole thing square, so it will be 1 minus omega upon omega n bracket square of that, okay, and square of this, so j square minus plus, so it will be plus square of this, so 4 zeta square omega upon omega n bracket square, correct. Now we'll separate the real part and imaginary part, and we'll try to see for different values of omega what are the 3 cases that we'll get over here. Okay, so first I'll write real part. Yeah, so it is 1 minus omega upon omega n bracket square upon 1 minus omega upon omega n bracket square whole bracket square plus 4 zeta square omega upon omega n bracket square. Then imaginary part. imaginary part very much clear over here. It is minus 2 zeta omega upon omega n whole thing divided by same denominator that we are having over here. One minus omega n, wait, omega n bracket square whole thing square plus 4 zeta square omega upon omega n bracket square. Right? So we'll go for the three cases. Case number 1, I'll say, where we are saying that omega is very less compared with omega n, and we'll see what is the condition. So when this omega is very less, this will be 0, this will be 0, this will be tending to 0 rather, right? So 1 upon 1 plus 0, so it is going to be 1. So I'll write gh j omega gain, gh j omega is equal to real part. Should I write it separately? It will be better. And so I'll write real part tending to 1, or I'll write ultimately it is going to be 1 only. So it will be easy for us to substitute. And when it is tending very large, the omega is very small means this is 0. So 1 plus 0, but this thing is becoming 0, so imaginary part will become equal to 0. Yeah. Okay. So now I'll write magnitude or gain, or I'll write directly gh j omega is equal to under root 1 plus 0, that is going to be 1. Right? And phase phi will be tan inverse of 0 upon 1, that is 0. Done. Case 1 is very simple one. Now we'll go for case 2. We'll go for the extreme condition first, and then we'll go for the mid condition. So let us say omega is very greater, very large compared with omega n. Then what is going to happen? Now this term, because omega is very high, this will start dominating. So I'll write real part. Now when this thing will dominate, it will be 1 will not be there, this term will be there, and this term will be there. So I'll write in short minus omega upon omega n square upon minus omega upon omega n square and square of that to raise to 4 actually, right, plus 4 zeta square omega upon omega n bracket square. Now see, in the denominator we are having 1 raised to 4 term and another one is square term. So definitely this term grows very faster when your omega increases, and compared with that this is very less because this is power 4 and this is power 2. So we are trying to approximate and we are trying to see where the value is going to tend, right? So because of that, if we neglect this term, we are going to have minus omega n bracket square upon raised to 4. That means omega upon omega n square of this minus and again square of this. Correct? So because power is 4, you will find that this is going to be plus. So instead of writing this thing, even if I write raised to 4, it will be okay, because minus n as if it is going to get minus minus is going to become plus. So just a minute. Yeah. So what I can write for this now is equal to two terms gone. So it is going to be minus omega upon omega n bracket square. Okay, so this becomes the real part of this for this particular case, right? Then we'll try to go for the what is the imaginary part for this, and then we'll go for magnitude and angle for this. So I'm talking about imaginary part now. See now, imaginary part, when your omega is very high, right? Then in that case, you'll find that this one will not come in picture. So this term is there and this term is there, right? So I'll write the thing minus 2 omega upon omega n upon. I'll not write that 1 now. So it will be minus omega upon omega n bracket square and square of this plus 4 zeta omega n bracket square. Now again the same thing, power 4 over here for the, just a minute. Yeah, for this term power is 4 and for this term it is square, so definitely we can neglect this term. And if you are neglecting this term, you will find power 4 power 1, so it is going to be equal to power 3, and in the numerator it will be minus 3. So I'll write it directly, minus 2 zeta omega upon omega n raised to minus 3. So we got the real part, we got the imaginary part. We'll try to square it and we'll see what is j omega we are getting. Yeah. So real part and imaginary part under root, just a minute. Yeah. So it is going to be minus omega upon omega upon omega n bracket square and again square of that, real part square plus imaginary part square. So it is going to be 2, I'll write in the bracket, minus 2 zeta omega upon omega n minus 3 and again square of that. Okay. Now we'll be able to see over here this term is very having power minus 6, so definitely it is going to tend to raised to minus 6 will be very low value compared with this, because it is going to be plus 4. So again very small value for very high omega, and we can neglect this and we'll have this thing. So ultimately we are going to get, see, square of this and then minus n will vanish and root will also get. So you are going to have omega upon omega n and whole thing raised to 2. So this is the whole thing raised to just a minute, I made a mistake or what? Minus 2 I am supposed to write. I think I have written 2. Oh, I made mistake over here. See, raised to 2, raised to 4, when it will go over here, it will be minus 2, right? And that's why it is minus 2. I forgot to write. That's what I was thinking. So this is minus 4 power and this is minus 6 power. We can neglect it. As omega increases, this will tend to 0 very fast. So we are neglecting this. Raised to minus 4, root to raised to minus 2. Now it's clear. Okay, so we'll try to get the gain in dB now. We got the formula for gain. Now we'll try to get it in dB. So 20 log of this. So you are going to have, yeah, So gain in dB is equal to what it is, 20 log to the base 10 of magnitude, that is omega upon omega n raised to minus 2. So I'll take this on this side. So it is minus 40 log to the base 10 for omega upon omega n. Right? That means if your omega is equal to omega n, then it will be 0. When your omega will be 10 times of omega n, so it will be 10, so it will be 1. So then the gain will be minus 40 dB. If it is 100 times of omega n, very large, no? So 100 times of, then it will be minus 80 dB. And in this way, right, when per decade the slope is going to be minus 40 dB per decade. I'll write minus 40 dB per decade. See, when it was real pole or 0, it was minus 20 dB per decade. For this factor, it became minus 40 dB. Just to remember, how to remember, right? I'm trying to tell you this thing. So minus 40 dB per decade. Now if you want to calculate phi over here, right? So for every decade rather, the change of the slope is going to be minus, because every decade the ratio will be 10 and the slope will be minus 40. And that's why the line will be of minus 40 dB per decade. I think this is understood, right? Okay. Then the next thing is phi, yeah. The imaginary part upon real part and tan inverse of that. So I'll write tan inverse of minus 2 zeta omega upon omega n raised to minus 3 divided by, yeah, the real part, that is omega upon omega n bracket raised to minus 2. Correct? So it is going to be tan inverse of 2 zeta omega upon omega n raised to minus 1. Okay. So see, again, when omega is very high, right, this component will die out very fastly compared with this. So this will be tending towards 0 by large amount. So definitely it is going to be tan inverse of 0 in that case. And that's why phi that you are going to get here, it is going to be minus 180 degrees. Tan inverse of 0, but minus sign is there. It's very well understood over here. See, your real part is having, the imaginary part is having minus sign, right? And because of that, whole thing will be on the negative side. And you're going to have minus 180 as the angle. Now the next third case, I'll write case 3. Yeah, when you are having omega is equal to omega n. Just a minute. When this thing is equal, we'll try to substitute in the real part and the imaginary part. So I'm writing for real part. See now, when they are equal, 1, where it is original, we should see to original one, right? So what I was saying, real part, this is 1, so 1 minus 1, 0. Okay, so real part is becoming 0. Then imaginary part, yeah. Now imaginary part, you see, this is 1, right? This is 1, so this will become 0, and this is 1, so it will be minus 2 zeta and this square bracket. So in the denominator, one bracket will remain. Am I right? Yes. So you are going to have and that is 1 only, so no need to worry. So it will be just minus 2 zeta upon 4 zeta square. So it is going to be minus 1 upon zeta. Sorry, 2 zeta. Yeah. Once again, I'll repeat. When this is equal, 1 minus 1, 0. So 0 in the numerator, so it is going to be 0. Then 1, 1. So 1 minus 1, this will become equal to 0. Right? 1. So this part will remain and this part will remain, which I have considered. Okay? So if I am trying to write for magnitude of GHA omega, then it is going to be, I'll write it instead of having a shortcut. Yeah, so it is going to be C. Real part to gaya, no need to worry, right? Imaginary part is just no need to write all these things, right? Ye 0, ye real part. So only this thing, and it is going to be 1 upon 2 zeta, or we can write it simply 2 zeta raised to minus 1. Then that is the magnitude. Now see, if the zeta value increases or decreases, then what is going to happen? So first I'll write gain in dB. So gain in dB is equal to 20 log 2 zeta raised to minus 1, that is minus 20 log of 2 zeta. Okay, so just I'll draw a small table and you'll be able to understand what is happening to the to these as the zeta changes, what will happen to the value of the gain. Only 3 cases we'll consider because those are very important, and based on that only the peak is going to depend. So let me write it instead of just speaking out. Yeah, and yeah, see now. Now what is going to happen if I am saying zeta is equal to 0.5? When zeta is equal to 0.5, right? 0.5 means 1, log of 1 is 0, so the gain is becoming 0. Alright. Gain in dB is becoming 0. If the zeta is greater than 0.5, see now what is going to happen. 0.5 is not visible, I'll write it properly. 0.5, right? This zeta is greater than 0.5. So if it is greater than 0.5, this value will be greater than 1. So whenever it will be greater than 1, log of greater than 1 will be positive and will increase definitely, and minus ka sign is there, so your gain is going to be more negative. So as zeta is greater than 0.5, gain is more negative. ठीक है. When zeta will be less than zeta will be less than 0.5. See, when this value will be less than 0.5, this whole thing will be less than 1. So that raised to, negative value. So you will find that yes, log of that is not negative, less than 1. So log will be negative. Negative will become positive. You just try on your calculator. Log of 1 is 0. Log of something which is greater than 1 will be positive. Log of something which is less than 1 is always negative. So that value will be negative. Minus will become positive, and here the peak increases. So we can say gain increases. Gain increases, and at 0.5, right? Because at exact 0.5 you are going to have it to be 0, but as soon as it will start decreasing, you will find that yes, there is peak you will be able to observe. When I'll draw it, you'll come to know. And when you are zeta, I forgot to draw one more column. Okay, let it be. Okay, otherwise if you can select this, yeah. So yeah, okay, best. So see, when I'm saying zeta is 0, right? Zeta is equal to 0. Now what is going to happen? As soon as this is 0, this is 0, log of 0 is undefined, infinity, and you are going to have gain to be equal to infinity. So this peak from 0.5, when you are decreasing on the, I mean 0.3, 0.2, 0.1, this peak will keep on increasing, and at zeta equal to 0, it will be infinity peak, right? Okay, this is one thing. Then last thing is the phase for this, right? So I'll write phi. I'll change the color. Let us see phi. Now phi will be tan inverse of the real part and imaginary part. Now real part is 0 and imaginary part is having some value. So it is going to be imaginary part is minus 1 upon 2 zeta, and real part is, wait, real part is 0, so it is going to be infinite, and that's why the angle is going to be minus 90 degree, right? Because in the negative direction of y. So what I'm saying now, see, so the three cases, just observe. First case, magnitude, where it is, g h j omega, magnitude is 1, right? Magnitude is 1 means in dB, when you are writing, it is going to be 0 dB. I'll write it in dB. It is going to be 20 log of 1, and that is going to be equal to 0 dB. So it will be a 0 dB line, and angle is also 0, so it will be just from origin till omega n is a straight line. At omega n something is going to happen like peak and all, we'll see what it is, but at that point the phase is 90, minus 90. So it was on 0, it is going to minus 90, and the last condition it is going till 180. In the previous pole and 0 single real, it was 0, minus 45, 90. So many of the things are parallel, just try to remember that, right? Nothing else. And then when it is increases with high value, it is becoming minus 40 dB per decade. In previous case it was 20 dB per decade. Yes, right. Now what I'll do is I'll draw both the plots. For see, we have derived it for complex poles, right? But for complex pole I'll draw, and exactly reverse mirror image of that I'll draw, which will be for the complex pole. So both Bode plots now I'm going to draw it simultaneously, right? Next to each other. I'm not going to do the derivation part for the complex zeros now. So let me save this. Yeah, clear. So let me insert the paper first. And we'll draw both the things separately, simultaneously. Yeah, best. Yeah. Yeah. It's okay, right? So I am talking about now, this is for complex pole, poles rather, pole एक होगा ही नहीं, complex poles. And this is for, if I can shift this, let me see. I cannot. Okay, let it be. I'll write in one corner. This is complex zeros. Okay. So let me draw the axis. Yeah. Okay. So this is magnitude plot. Omega on the log scale. Phase plot. Phase plot. And omega. Yeah, I think this is sufficient. What we are going to get is gain of 0 dB. We got this line, and in the derivation part we had seen that minus 40 dB के gain से the thing is going to decrease, right? So I'll take that minus 40. Let us say this is the point of minus 40 dB. Now you divide as per your requirement the scale, right? And let us say this is omega is equal to omega n. N not right over here. I'll just mark that point. Omega is equal to omega n. Alright. So what we are seeing initially till this point, it is going to be a straight line. Okay. I am talking about the ideal case now first, and at this point 40 dB ka decade. So this is the point through which it is going to pass, right? So you are going to have per decade 40 dB. So I'll draw that line also. Yes, but now something is happening at this point, so we want to mark that thing, right? At omega equal to omega naught, what is going to happen when omega is equal to omega naught and zeta is equal to 0.5, then definitely this will be the curve. So just, I mean, approaching from this value from 0 till 0, then in that case it will be just a straight line actually, right? And when zeta is equal to 0.5, and this will go. But if zeta is not equal to 0.5, let us say zeta is less than 0.5, whatever might be the value, I just write it, zeta is less than 0.5. We had seen that if zeta is less than 0.5, then there is a peak at this point. So this point is when your omega is very very less than omega n. This is equal, and this part of the frequency when omega is very high, right? So what is going to happen now with blue? I am trying to draw the curve, at this point you will find, yes, a peak is there, and then it is going to follow this line. Yeah. Okay, so this is going to be the exact or actual curve. I think okay, if you want, I'll draw the slope of this line also. That is going to be equal to minus 40 dB per decade. Correct. Now if we are talking about the phase plot, we had seen that the angles that we got was 0, minus 90 and minus 180. So I'll draw those lines. Let us say 1, 2, 3, 4, 5. This is 90 and 1, 2, 3, 4, 5. This is 180. And I'll draw the curve with this. Yeah. So I'll write, yeah, this is minus 90. This is minus 180. Correct? And initially it is 0. And when omega is equal to omega naught, the angle is minus 90. Okay. So again the S curve, I'll try to draw it. Going towards this. So this will be the phase plot. Now exact mirror image of this, I am going to draw it over here. And let us say this is kitne, how many 1, 2, 3, 4, 5, 6, 7. Alright, so let us say this is plus 40 dB. Okay, and 1, 2, 3. 1, 2, 3. So this one is omega is equal to omega n. This is omega very much less than omega n and on higher side. Alright. Now till this point you are going to get a straight line. So I'll draw that. Yeah. After that it should be plus 40 dB ka slope. So this is plus 40 will be over here for the next decade. And a line passing through it we are supposed to draw. So I'm drawing. Alright. And I'll write over here slope is of 40 dB per decade. Plus 40. Correct. And the exact curve if you want to draw. Now when your zeta is on the lesser side, you will find that yes, the peak will be on the, it will be more negative, right? And the peak will be on minus in towards minus infinity. So if I want to draw it approximately, it is going to be this and going along this line. Okay, so I'll write zeta greater than 0.5. So now we'll go for the next thing, and that is we have to draw the phasor plot also. Just a minute, we'll draw it. Yeah. Now let us say I'll make change in the color here. Let us say this is 90 and this is 180. So I'll write it over here, plus 90 and 180 degree. So at this point, let me draw the point. At this frequency, it is going to be 90. So I'll draw the curve. See, this one is exact mirror image of this on the same line. This one will be exact mirror image of this. So it is going to be 0, and on this side it is tending towards 180. Yeah, so all the individual parts we had seen, right? We have to summarize the thing. We'll summarize it in the last, but before that I would like to I would like to take the characteristics. Okay, let me save this. And not required now, so I'll say delete. Okay, so now we are going for the next thing, that is the frequency domain characteristics or frequency domain specification. Both the things are same. Frequency domain specifications. और करेक्ट, जैसे जैसे we were seeing the specifications for time domain, right? TRTP and TS, right? On the same line we'll see the frequency domain characteristics now. So see, the standard characteristics of an ideal low pass filter first I'll draw, and you will find that yes, those characteristics are same as that of our normal closed loop control system. So what are those characteristics? So I'll write it over here first. First point, standard characteristics of low pass filter. Now, low pass filter means, I think when I have explained you the Bode plot, I definitely explained you what is this thing, right? Why we are talking about low pass filter. See, first I'll draw the low pass filter and then I'll explain. Just a minute. See, when you are talking about low pass filter means, if I'm talking about the magnitude curve, okay? Yeah. So I'll write. क्या बोलेंगे हम, मैग्नीट्यूड प्लॉट. Okay, and ideally what we want, gain to be equal to 1 for the system, because just I'll tell you, I should not draw with the same color. Let me change it so will be more easy to understand. So let us say, yeah, this is low pass filter characteristics. कैसे है? What we are trying to draw, on this axis you are having magnitude. This is magnitude 1, this is magnitude 0, right? मतलब over here it is 0, right? And this thing is your frequency. Now I'll not write this 0 over here because it may confuse. Alright, now see what is happening at lower frequencies. System gain is 1. On higher frequencies, you don't want it to be considered by your system, or your system should not pass it. So only low frequencies are getting passed, and you are having it. And the same thing is with our control system. Basically, same characteristics will be there for the control system also on lower side, right? Because the input is having low frequency, on lower side you want, yes, the gain of the system should be equal to 1, and on the higher side noise is going to be there, you want to filter out it, so should not pass. Okay, so I'll write frequency frequency range of our interest. Correct? And this frequency range is noise. Definitely we want to filter it out. Correct? And same thing is with our control system. We want on lower frequency ESMI system to work, right? And should have gain 1. Now why gain should be equal to 1? Because what is that gain 1, right? At this point you will find gain is 1. That means output is following the input perfectly, and we want that. Whenever you are having change in the input, you want that much change in the output. So whenever gain will be equal to 1, right, that means the magnitude is 1, and that means proper tracking is there in your system, you know? So I'll write for this one, I'll write in short proper tracking of, or I'll write magnitude 1 का मीनिंग है आउटपुट follows input, and that is proper tracking is there. है ना? Correct? Yeah. Then the next thing is, this is the frequency, right, where your gain is becoming 0. So that is called as cutoff frequency actually. Correct? So now we'll see some of the characteristics. Now see, ideally, this is ideal. Ideal thing is, ideal characteristics of low pass filter are not practically realizable, right? So we should think of typically what it is. So I'll add second point, typical control system characteristics. Okay, so if I want to draw the characteristics, let me draw it first, so the idea will be more clear for you. See, ideally these characteristics are like this. Yeah. Okay, so again, this is magnitude and this is frequency. So magnitude plot we are talking here about. Now you'll find that yes, at this point the magnitude is maximum. Correct? This thing is called as, this frequency is called as omega r, or sometimes you will find yes, it is denoted by omega p also. Both the things are same. Whatever peak that you are getting, right? Why omega r? This is called as resonant frequency. The frequency where the magnitude is maximum is resonant frequency. Then the maximum maximum magnitude that you are getting, that means it is denoted as MP, peak overshoot, or it is also called as MR, resonance peak. Right? Both the things are same. And this is point 1, where gain is 1. Right? So initially for the system gain is 1, might be for some of the frequency it is increasing, again it will start lowering down. So we want to cut off this. Now theoretically 0 is possible, practically you cannot have gain to be equal to 0 for the system, right? So we have to put some restriction for some value of that gain, and keep in your mind that gain ka value is considered as, I'm drawing it over here, right, and then gain is 1 upon root 2. Okay, and the point at which gain is becoming 1 upon root 2, this frequency is called as omega c. And see, so cutoff, after this cutoff is there, and whatever is the frequency range which is available for which gain is higher than 1 upon root 2. 1 upon root 2 means it becomes 0.707. So say 0.707 say higher gain for whatever frequencies for which you are going to get that much gain. That is called as bandwidth. Okay. So one is bandwidth. Then the second thing is I have told you, I'll write instead of just saying. Yeah. So we are talking about the characteristics. Now I tried to explain you the characteristics. I'll write also, so will be easy for you to remember. So number one, either you can say omega r, or it is called as omega. Some books you will find omega p, some books you will find omega r. This is resonant frequency, or it is also called as peak frequency. Correct? Both the things are same. The frequency at which magnitude is maximum. One. Right? Second thing is the value of the magnitude, maximum gain that you are having. So I'll denote it as MR or MP, that is maximum magnitude. Okay. Then the third thing is low frequency range, high frequency range are defined with respect to the bandwidth. System ka low frequency and high frequency is what? Right, that depends upon bandwidth. So what is bandwidth we should know, and it is denoted by WB, bandwidth. Range. So what is bandwidth? Bandwidth is the range of frequency over which the magnitude will not be below 0.707. That means if I want to write, I write gain should be greater than or equal to 1 upon root 2, that is 0.707. Now if you want to write this thing in dB, it is going to be, I'll write in dB, it is going to be equal to 20 log of 0.707. That is equal to minus 3 dB. So it is equal to minus 3 dB. Then the next thing is cutoff frequency, omega c or omega 0. Okay, so practically sharp fall in the gain is not possible, right? So we used to say below 3 dB. Whenever the frequency reaches 3 dB, below that, yes, that is the cutoff frequency. So I'll write frequency at which magnitude is is 3 dB below. That means this point. After that, yes. So this point is the cutoff frequency. Okay. So